On today's show, space is the place, as we are joined by our tour guide to the cosmos, author and professor Lisa Kaltenegger from Cornell's Department of Astronomy. As founding director of the Carl Sagan Institute at Cornell, Lisa says we are closer now to discovering life in the universe than we have ever been. We talk about exoplanets, deep space exploration, and the multidisciplinary science involved in identifying potentially habitable worlds. We also discuss her fascinating brand new book called Alien Earths, which is available now from Macmillan. So see the episode notes for links on how to get your own hardcover copy. Prepare for liftoff, listeners. Here's my conversation with Lisa. Lisa, let's cut right to it. So in recent interviews and the hype surrounding the book's release, you suggest that we are now closer than we've ever been to discovering life out there in the universe. Why is that the case?
What's amazing, what has changed, is that we know that 1 out of 5 stars has a planet that's at the right distance, so not too close to the star, not too hot, and not too far away from the star, so not too cold, in this, what we call the habitable zone, where you could have liquid water on the surface of a rocky world like our own Earth, and the planets are small enough to be rocks like our own. And so that has rewritten how we understand our place in the universe. We live in this golden era of exploration, but not just that, because we launched the James Webb Space Telescope. So it's about 4 times my size in space, and for the first time ever, we have an instrument that can collect enough light to look at these small worlds and figure out what's in the air on this other world and whether or not there are signs of life in it.
The anticipation around the Webb's telescope's deployment and actually the success, right? When we first saw those images, you must have been as stunned as delighted, probably more so than most people.
Absolutely. I think like all around the world, astronomers were doing a sigh of relief because there were so many single point failures. So, with such an incredibly complex technological project like the James Webb Space Telescope that brought together ideas from all over the world to succeed, everybody was working together. There can also be things that go wrong. And so the first images showed us that we had beaten the odds, that altogether we had a new view of the universe.
You are creator and director of the Carl Sagan Institute at Cornell. Just for a little background, right? Carl Sagan is a globally famous astronomer that did serious work at Cornell in his time, during his tenure. I think it was back in the 70s, right? Was mostly when he was working, 60s also, I suppose. So you opened the Carl Sagan Institute. You created it. By design, the Carl Sagan Institute is made up of people who are working in a variety of disciplines, and at Cornell, across multiple colleges, right? So you have people, not only scientists, not only astronomers, cosmologists, et cetera, but people from a variety of disciplines. And that's the way you kind of wanted to build it. Can you tell us a little bit about how you all work together and what you're trying to achieve?
So the key thing is we have these new worlds around their stars, so another sun, and trying to figure out if there could be life on them requires the knowledge and the ideas from many different disciplines. Like, you wouldn't be able to find signs of life if you don't include the biologists, the chemists, the geologists, the astronomers you're looking for, the engineers, the remote sensing people. And so I basically see this problem as finding another world, finding signs of life on another world as this intrinsic big puzzle. And so it's just natural to put people together from different fields to actually figure out some of these puzzle pieces and then interconnect them so they can put them together in this big overall puzzle that is us trying to find out if we're alone in the universe. And the way that this worked at Cornell is when I came here, I was like, oh, I'd love to work in an interdisciplinary, so many disciplines, institute here at Cornell. And then when I said that, they were saying, well, if you think it's important, you've got to build one. And this is how I became the founding director of the Carl Sagan Institute. And they are incredible colleagues from all the different departments that first I lured with really good coffee and chocolate and this idea of trying to find life. And we together building the toolbox to spot life on other worlds in our solar system and also worlds that circle other stars.
I visited the Space Sciences building for the first time the other day when I came over for coffee last week. And I was struck by the space that you all work in. There's everything from meteorites, published research on the walls. It's a very visually stimulating place. And I see a lot of activity. Now, and there were people that appeared to be working in a variety of disciplines, just kind of in the way that things were set up. Any people that are on your team that maybe deal in the abstract, I don't know, people that are involved in some of the other arts or sciences that you may not expect would be on your team. People that have to use imagination, start theorizing in new ways.
Absolutely. I think the art is even wider than that, because I have people in my team in collaboration with other departments where, for example, in one of them with the microbiology department, we grow different kinds of life forms that live in niches on the earth, but provide these brilliant colors. Like, for example, if you go to Yellowstone National Park, you see these colors, what are life forms adapted to this hot sulfur springs. And so we grow them, and then we go to another department, remote sensing, civil engineering, where we actually measure what the reflection of light would be. And then we put them in our computer programs where we build a puzzle piece of this planet and how it would look like to my telescopes, where the astronomers then compare that to light that we collect, for example, with the James Webb Space Telescope or the upcoming Habitable World Observatory. So we're doing design work now, and we need to know what we should be able to find. And we're going from, really getting your hands dirty, like doing the biota or trying to melt planets in another lab where we're trying to figure out how molten hot lava worlds would look like to our telescopes, to people who have to bring this together, and to people who have to consider just completely different forms of life. What about if you didn't have liquid water? What about if you had a methane and ethane lake? Could you still make vesicles? Could you still make cells? And so everything's in there. And then we also have people from science communication, from performing art, from music, who love this idea, because our search for planets out there in science of life also is a reflection to where we are in our society, in our wisdom, in our curiosity about the cosmos and our place in it.
Yeah, and that's a testament to the work that you do at the Institute, which is you kind of have a gravitational pull going on, right? And so you are able to pull people who are capable of that abstract thought, communication, arts, performing arts even, right? I just find that totally fascinating. It's got to be a riot.
It's a riot. We're having the best time and the best coffee on campus. So if you're interested, we have the best coffee
everywhere
on campus.
I went over that building, I saw coffee makers everywhere. It's kind of straight out of central casting, to tell you the truth. If you would imagine like a space science unit, better have that coffee going.
I agree. But
it's really something.
The interesting thing is like the discussions, the talks we have, the ideas that fly through that room when we meet. That's really where the most interesting and the most fun parts are of the job.
So the tech is really important. So I want you to paint a picture for me as to what are the tools that you're using. We referred to the James Webb Telescope just moments ago. What else are you using? Diagnostic observational equipment? Is it mostly space-bound, like the telescope itself? Are we using earthbound tech? A combination probably of all of them. But tell me what you look at every day or what your team is monitoring to look for life on other planets.
So absolutely. Maybe let's go one tiny step back and just talk about how we found these worlds. Because a planet is tiny compared to a huge, huge, huge star. And basically what you see is this huge sun. And if you put the Earth 100 times next to each other, roughly, that's the diameter of the sun. And even fluctuation or storms on the solar surfaces are actually larger than our own planet. And so basically trying to find such a small planet next to such a huge, bright star is incredibly hard. So most of these more than 5,000 worlds that we discovered around other stars, we've never seen. And so we've spotted them because these planets still have an impact on their star, and we can see the stars. So one of the methods, the first planet ever found, is actually when the star keeps the planet going around it, the planet also tugs on the star. And so the star moves back and forth in counter movement to the tug of the planet. They move around the center of mass. And you can think about it a little bit that if you go to the park and you walk a dog and the dog wants to go somewhere you don't, then you have to lean back.
Yeah.
And you don't have to see the dog to know that something is pulling. And so in the light of the star, we can find these planets. And if by chance, and that's just really a chance alignment, that planet actually goes in front of the star from our point of view and blocks part of the light from the hot stellar surface, then the star becomes ever so little bit dimmer. And that's frequent. And so for the Earth, it would be once a year for about 13 hours. That our sun, if you see it from outside and see the Earth's blocking light, would just appear a little bit dimmer. And so we found thousands of planets that way. And what do? So now we found these worlds. We can figure out from how fast they move around their star, how far away they are. These are Kepler's laws applied. And so basically what we do then is to say, okay, so this one will kind of be warm enough in this habitable zone that I was talking about.
You can deduce that from this observation, the simple distance from the sun, speed,
Exactly.
velocity. Okay.
You basically know that a certain speed, a certain distance from the sun, it requires a certain speed to go around the star. And so the speed I can measure because I know when the planet keeps coming around. And thus I can calculate how far away it is and how hot it must be there. But when the planet goes in front of the star, part of the light from the star also gets filtered through the planetary atmosphere before it gets to me. And we've been doing this for huge planets already. So the huge planets like Jupiter have like a lot of gas. And if you compare Jupiter to the Earth, Jupiter has massive gas ball. The Earth is a small rock. And all these beautiful patterns on Jupiter are really weather systems. And in some of the storms on Jupiter, the whole Earth would fit in and there would be space to spare. So we've trained with Hubble and other instruments on the ground how to read the atmosphere of these giant planets with lots of gas. And now with the James Webb Space Telescope for the first time, we can look at the light that basically gets filtered through the atmosphere of the planet when the planet's in front of the star, gets to my telescope. So a really small signal. I split the white light up in its color, so say red to blue, and I figure out if in each color I have enough energy. If energy is missing, that means the light hit a molecule on its way to me, and the molecule started to swing and rotate. Thus, the light didn't make it all the way to my telescope. So like a passport stamp, which light doesn't make it to my telescope tells me what the chemical makeup of the air of this other world is. And this is where my team, or the whole Carl Sagan Institute team, comes in. So what does it mean? What can we see? What does it mean? Can I explain this without life? Do I need to invoke life to explain what I see? And then if we talk about this, what kind of life? There are so many different kinds of life on the Earth. What do they produce? How could we spot them? How could we not miss signs of life if they're just a little bit different than here on the Earth?
So we talk about, in layperson's world, right, our understanding of it seems to be limited to there may be carbon there may be water, there's evidence that there was ice on Mars, those kind of things. So it's always the water. Why carbon and water? Are we certain that those are the two things necessary to sustain life?
Well, we do know, sample of one, our own planet, that we have carbon and water, carbon scaffolding, and then water as a solvent. And so the easiest way and the simplest way is to look for that somewhere else. And if you look at it in detail, it actually makes sense because carbon can build really, really long molecules, complex molecules, but you can also easily break it energetically. So it means you can recycle it incredibly effective. Other things like silicon is actually much, much harder to break after. You can make complex molecules, but you cannot break them after. You would have like a lot of energy to do that. And then also, if you're going with water as a solvent, you're going to have some water. And that water is H2O, so hydrogen and oxygen. And so when you combine carbon with oxygen, you get CO2, a gas that's soluble in water. If you combine silicate with oxygen, you get quartz. So that you have to heat up like crazy amount to get it back into a gas form to be able to reuse it. And so it seems to be that carbon scaffolding and water are two very good bases for life, for complex chemistry and complex chains in a solvent. But of course, when you get too far away from the star, then the water would actually freeze. Mm-hmm. And we're hoping that other solvents like methane or ethane, like on Titan, could actually take over and provide another base for life as we don't know it. And this is why we have missions also going to Titan, like the Dragonfly mission is going to fly there and sample the surfaces to hopefully find something that we can't even really imagine yet. But so far, when we're looking, we have to look for something where we understand that this is a unique sign of life. And then we're going to keep our eyes open for anything interesting and weird.
Hey, little diversion. So I looked at some imagery actually right outside your office of Titan. Not sure if it was photographic or spectrographic or whatever. It's a moon that's full of methane gas lakes. What's the deal
Absolutely.
there? What do we know about Titan? And why are we having a look?
So what's really interesting is like the further away you go from the sun, the colder it gets, right? You're further away from this hot sun. But what we found out is that there are a couple of really interesting moons in our solar system around these big gas giants. And those moons could potentially have habitable environments.
Oh.
So two of them, Europa and Enceladus, are icy moons. They have a huge ice layer, but below a liquid ocean. And it is because they get basically pulled and pushed by the other moons in the system. And so like kneading a dough, it gets hot. And so it melts the subsurface ice. And so you have oceans. But there's another place, Titan. And Titan is this gas-rich atmosphere moon. So it's a moon, it's a rocky moon, but it has a pretty dense gaseous atmosphere made mostly out of methane. And the lakes are like methane and ethane lakes because it's too cold. Water freezes out at that distance, but other liquids do not. And so there the idea was born is like maybe a completely different chemistry, or at least, a different solvent could actually provide habitats on Titan. And we don't know yet, but we know that it has liquid lakes and oceans on Titan. And the next way is to explore because we can reach that one.
A reason to investigate further. So tell us a little bit about some cool exoplanets. I don't know, any greatest hits that you have? You had mentioned that we have discovered thousands of planets. When we talk about an exoplanet, just for clarity, are we talking about a habitable planet or what?
No, we're actually talking about planets that are completely different than ours, and some of them similar to ours, but we're talking about huge gas balls, two small rocky worlds. But some of these rocky worlds are so close to the star that they are so hot that they would have lava oceans on top of it because it's just so much heat from the star hitting them. And so when you look at what kind of planets we found, you actually see that most of the planets that we found are bigger than the Earth. The Earth is the biggest rock in our solar system, but smaller than Neptune. So Neptune is the smallest gas ball in our solar system. And what we found in the search is that the most common planet out there around other stars is actually one we don't have in our solar system. It was a huge first surprise. But this is where science is fun, because you want to see something that you haven't expected, because that's where you learn. But with more and more time, we're starting to get to similar planets like the Earth around or planets that could be like the Earth around other stars. Because, of course, it's much faster to find planets that are close to their star because they only need not even a day to actually go around their star. They're whizzed around their star in like 18 hours. And so that one you can find in 18 hours. But an Earth, you need at least a year to catch it once. And so there's also a bias in what we have found so far. And that bias is what's easiest to find. But what's really exciting about this is that tells us that we're just seeing the tip of the iceberg. And then there's going to be so much incredible variety. And you talk about the weirdest world, and you talk about the weirdest world. So let me just pick a couple.
Yeah, things that kind of blow your mind, even Lisa
Absolutely, that blow your mind. So one of them is these rocky worlds that are just whizzing around their stars in about 18 hours. So everything's going to be so hot that you melt any rock we know. And so you would have lava oceans covering this. And you can think about tides because it's so close to the star, and like magma waves that kind of slash around the whole planet. Other worlds that are crazy in a way are worlds that get like pushed out initially when there's like lots of going on in a young planetary system. Sometimes there are collisions. And so they are lonely wanderers out there that lost their star and are basically in the cold isolation of space on their own. And there are even planets that actually where the star died. So the star exploded. And the only thing you have left over is the stellar husk, the stellar corpse. And yet even there, we have found planets that survive that fiery end of their star, what is not something we had expected at all. But there's this planet happily orbiting what we call a white dwarf. So the residual of an exploded star, and it's there. And so that, of course, asks the question, so how tenacious is life? If the planet can survive, could, if there were life survive as well?
I like the creativity involved in speculating on the way that life might manifest itself or represent itself. Like in the case of, you had mentioned this earlier about fungi, creating fungi. Tell us about the pink fungi. I just got to know a little bit more. By the way, this was kind of a point of focus in some New York Times article that you did just from last week. We'll share the URL because I think that's really cool. Congratulations on that. Tell me about the pink fungi and creating what you think could be life forms on other planets. It's tough to imagine for some of us.
What's really interesting is that sometimes when you go out and see all this green vegetation, plants and trees and everything, a lot of times it's easy to get stuck to think, oh, that's what we're going to look for. Everywhere else is going to be green. But then when you think back and you know about our own planet and how much it has changed, then you realize that there's a lot of diversity of life that was throughout Earth's history. But even now, when we're talking about Yellowstone National Park and all the gorgeous colors you see there, and that some of them are like mass biota. And so what we have built here at the Carl Sagan Institute is a color catalog of life. And it basically is just having a look at the most diverse places on the Earth and having a look at life, collecting some, growing in the biolab, and then having a look at the reflection to say, like, if another planet would just be a little bit different, not to miss signs of life because we're looking for green plants. And today we have a paper out that's led by one of my postdocs that says, like, purple is the new green because there are other biota that's much more adapted to many different environments than the green photosynthesis that we usually see around us all the time. And so how did they get to pink fungi and trying to overtake the campus? The New York Times reporter, she was super amazing and sweet. Yeah. And she was like, so what's the weirdest things you ever grew? Yeah. And I was like, well, the weirdest thing we ever grew was actually a pink fungi. And the funny part is, like, I remember this to this day because we're trying to do the most diverse life that we can get, right? From all the different parts of the tree of life and so on. And so one of them is fungi. Fungi are great.
Yep.
But they contaminate everything if you don't know what you're doing.
Right.
And so once in a while, I go to the biolab and I remember they were like, Lisa, do not touch this because the fungi is going to just contaminate the whole lab. And I do not, when I'm warned, I do not touch stuff that I'm not supposed to touch. I learned enough. This is why this interdisciplinary network of scientists is so important because I kill most stuff that I grow. But also, it could be that the astronomer in the room opens a flask that they shouldn't open, right?
Yeah.
So I leave that to my amazing microbiology colleagues to do this. And then we take what they've done and measure it. And the pink fungi, which is one of the fun examples where we was like, be very, very careful because the spores of the fungi go everywhere. And I'm like, learn something. Be very careful. Spores of fungi go everywhere.
You and I survived the potential pink fungi
there was no
contamination.
There was no pink fungi, I learned. We did well. And I'm kind of worried about a phone call now that the university is kind of like, excuse me, you're doing pink fungi?
Okay. All right. So let's say one day you wake up to find that your team has discovered what appears to be a habitable exoplanet or moon. Now, what do we do, right? So I had thrown this scenario where I imagined human beings acting on their worst instincts. Suddenly, the military's involved, NASA's involved, and, we're preparing for war because that's kind of the way we are. That's at least that, I've seen enough science fiction to think that may be the way we are. What do you do, right? So you say, boy, I think this looks like a good lead. What do you do?
Well, the most exciting thing about this is, like, if we found such a signal, I hope we will, but I don't know yet.
Yep.
Hope we will. That's what we're working towards. Then what do? Is you restart your computer, right? Just to make sure that there's not
cold
everybody
reboot.
Knows that cold reboot, just to make sure that there's not some hang up.
Okay.
And then, as always in science, what you do is you share that information. Because first you put your own criticism on it, like the worst thing you can even do, like just taking it apart, picking it apart, saying, maybe this is really not this, maybe I'm in an error here and here. And then you share the data for somebody else to do the same thing, just to make sure that what you're seeing is not something you want to see, but that's something that's really there. So the scientific method, in a way, beautiful hypothesis, ugly fact, somebody call it the big tragedy of science, but it's what lets us distinguish our wishes from what's really there. And so what do we do next? Well, next we celebrate. It's like, if the other team also finds it, then we tell everyone. And your scenario, the great thing about your scenario is that actually these planets and their stars are so far away and we have no way to travel. So we can actually celebrate finding this and then thinking about what it would mean for everyone, without having the fear that, oh my God, now we're going to destroy that world. Because as a scientist, if I find it, there's no way I can control who gets to go.
You said this to me when I was in your office. You said, Chris, there's time.
There is time.
This could be hundreds of thousands of years ago and that place could be gone.
That is true. But also the cool thing is I think it's just re-established, or it's going to remake our worldview because we'll know we're not alone. And then the next thing we do is to figure out how to contact or how to go there. But that's a decision we all have to do together because we all have to be comfortable with that approach. And in a way, from my work, we're looking at gases in the atmosphere of a planet, how the biosphere changes a planet and what I can spot. If you looked at the Earth from far away, for about 2 billion years, you could have told, just with our level of technology, that there's life on our world. So in a way, the cat's out of the bag. I don't think anybody's going to come and eat us just because we send a signal.
Right.
However, I'm an optimist, so the good thing is people have to decide together if we ever want to make an active signal that we send out. But this passive search, trying to find signature of a biosphere in the air of another world or on the surface of another world in terms of colors, that's something we can already do to figure out what's around us and how we fit into this beautiful cosmos.
So in the absence of discovery of life or having leads on potentially habitable planets, in what ways do you feel like you might be making progress in your methodologies, in the science that you practice, that kind of territory covered? Do you still feel like that, right? Because there's there's impression that you're doing the stuff and now we're waiting, but it's not like that.
It's not like that because what is so amazing is that for the first time ever, we have a telescope that can collect enough light from these small rocky worlds that at the edge of technical possibility, it's so hard to do. But we are collecting the light right now from planets in this distance in the habitable zone. And we have to read it. We have to figure out what it actually means. And all these building blocks that we've put into place, trying to understand how a rocky planet works, how a biosphere could change a planet, how we would see that in the light of the telescope. All this now comes together. And this is also why I wrote the book now, because we have entered this new era where for the first time ever, we have a telescope that can do this at the edge of possibility. So it's really, really hard to do. We're not going to be able to do this tomorrow. But by adding up the signal for a couple of months, for a couple of years, we're going to beat the noise. Remember the star, how big it was? And it is kind of has eruption on the surface. So we have to beat the noise that the star adds to our data down to see the tiny signal in the atmosphere of another world. But for the first time ever, it's possible.
You must be excited beyond measure. Let's talk about the book a little bit. I love the voice. I feel like when I was reading it, I heard this voice. Who were you trying to reach when you wrote this? When you set out, what was the objective that you were trying to achieve? And tell me a little bit about the audience and who you were trying to reach and why.
Absolutely. So I had a sabbatical. That means it's a year where academics can go and think about what they're doing and what they want to do next. And so I decided to write it down and try to figure out what I've done, how the puzzle pieces fit. And the easiest way to figure out if you understand something is to explain it to, my mom or the neighbor down the street. Mm-hmm. And then you figure out if there are holes in what you know. And I was like, you know what? It's like, I want to talk to somebody about this. I want to talk to most of my friends, from back home, from Austria, they don't do science at all. I want them to figure out why we're living in such an exciting time. And so this is how I started to write this book. And I also want the people who might not see that there's a place for them in science, whether it's young women or just people who think, oh, there's nobody who looks like me. I wanted him to hear a voice from a young woman in science that is at the forefront and that says, no, you know what? You need as many diverse ideas as possible because these problems are vast. Having different opinions and points of view help you. And then the other thing, of course, is I love science fiction. And so I was like, so which of these worlds could be real? Because that's a question I get a lot. And so I take some of these different worlds, like Tatooine, for example, with its two suns, and I'm wondering where the second shadow is. And while I was reading this, it was becoming more and more interesting because I know Alistair Reynolds, who's an amazing sci-fi writer in Britain. And so we know each other from when we both were working at the European Space Agency. And he asked me for advice on some of his planets once in a while. Sometimes I get acknowledgement, so he's super nice about this. And then I got to know Andy Weir. And so Andy was like, so, the person who wrote The Martian and now wrote a really fun book that's called Hail Mary, where we make contact.
I listened to that audiobook. Loved it.
Oh my God, loved it. And the thing is like, he was like, so the planet that I admitted there, does this make sense? I thought about this and this. And I was like,
he ran all that by you?
Well, after the fact. And I was like, that part works and that part didn't. And so he said, well, next time he's going to call me first. But it's just fun to think about the visions that we have about these worlds and which ones could be reality. In some of the worlds we found out there are actually weirder than the ones that we've envisioned in sci-fi. And for example, Tatooine, one of my friends said I destroyed the movie for her forever, what I didn't want to do, because I was just asking, where the second shadow?
I'm never going to be able to watch that film again with the same, right? You've ruined, thanks.
George Lucas, next time,
You've
Spielberg, they just all need to call me.
Lisa Kaltenegger, you set me on a path of discovery. I'm so excited to have met you and have read your book and learn a little bit more about the work that you do at Cornell. I hope you sell billions and billions of books on your tour. Thank you for coming by today. It's been lovely.
Thanks so much for having me. And I just hope that it shows people what amazing time we live in and connects them back to when they look up at the sky to a different kind of feeling of being connected to the cosmos.
Thanks for listening to Cornell Keynotes. Be sure to check out the episode notes for information on our Spaceflight Mechanics Certificate Program and many more at Cornell University. Thanks again, friends, and subscribe to stay in touch.